The topic today is kinetics, specifically the integrated rate laws. In this video, we will discuss the integrated rate equations. There are actually videos in this series. In this first video, we'll talk about the integrated rate law equations. The second video talks about using the method of integrated rates to determine the rate law and the rate constant. The third video will discuss half-life. And finally, the last video will give an example problem of using the integrated rate equations to determine the concentrations of reacting species at later times. Recall from our previous video on rate laws that the rate law gives the relationship between the reaction rate and the concentration of reacting species. For a reaction between A and B to form products, the rate law would have the general form rate is equal to K times the concentration of A raised to some power x times the concentration of B raised to some power y. In this equation, K is called the rate constant, and x and y are called the orders of the reaction with respect to reactants A and B respectively. Remember also that all rate laws must be determined by experiment. What are integrated rate laws, and how are they different from the rate laws we're talking about? The integrated rate laws are equations that describe how the concentration of a reactant depends on time as the reaction proceeds. There's a separate equation for each reaction order, 0, first, and second. These equations were derived using calculus from the rate laws. The table on this slide will help us organize and summarize what we learn about the integrated rate equations. Let's start by looking at a graph of concentration versus time for reactions that are 0, first, or second order. If we start with the zero order reaction, we see that the concentration of A decreases linearly with time. We've already shown that the rate law for this equation is that the rate is equal to K times the concentration of A raised to the 0 power. Remember though that anything raised to the 0 power is 1, so this simplifies to the rate is equal to a constant, the rate constant. If you integrate this rate law with respect to time, you get the following equation: that the concentration of A at some time t is going to be equal to negative K times the time plus the initial concentration of A. As we've already seen, plotting the concentration of A versus time for a zero order reaction yields a straight line. If we look at the integrated rate equation for a zero order reaction and compare it to the standard equation of a line, we see why it turns out to be linear. Since we're plotting concentration of A on our y-axis and time as on our x-axis, we get a slope equal to negative K and a y-intercept of the initial concentration of A. So now we can fill in the rest of the first row of our table. For a zero order reaction, what type of plot will give us a straight line? The straight line plot will be when we plot concentration of A versus time. The slope of that plot will be negative K. What should the units of K be for a zero order reaction? Let's look at the rate law for a zero order equation. We have rate is equal to K. The units for rate are always concentration units, usually molarity, per unit time. Another way to write that is to show the time as having a negative exponent. Since the rate is equal to K, our K units must have the same units. Now let's look at first order reactions. When we look at the concentration versus time graph for a first-order reaction, we see that it is not linear. It is curved. The rate law for a first-order reaction is rate is equal to K times the concentration of A raised to the first power. If we integrate this rate law with respect to time, we get an equation that shows that the natural log of the concentration of A at some time t is equal to minus kT plus the natural log of the initial concentration of A. When we plot the concentration of A versus time for a first-order reaction, we see that the result is not a linear plot. It's curved. If we compare, however, the integrated rate equation for a first-order reaction to the standard equation of a line, we see that we can obtain a linear plot. A linear plot is obtained by using natural log of the concentration of A as our y variable, still time as our x variable. In this case, we'll get a straight line where the slope is equal to negative k and the y-intercept is equal to the natural log of the initial concentration of A. Let's fill in the second row of our table. What type of plot will give us a straight line for a first-order reaction? We've just seen that we'll get a straight line when we plot the natural log of the concentration of A versus time. Again, the slope of this plot would be equal to negative k. What are the units of k? Well, this time we have a new rate law. Rate is equal to k times the concentration of A raised to the first power. The units on rate are concentration units per unit time. But on the right side of the equation, we have a concentration value. What do we need the units of k to be to make this statement true? K has to have units of 1 over time. What about second-order reactions? These also give a curved plot when you plot concentration versus time. The rate law for a second-order reaction is rate is equal to K times the concentration of A raised to the second power. When we integrate this equation with respect to time, we get 1 over the concentration of A at some time t is equal to 1 over the initial concentration of A plus kT. Again, plotting concentration of A versus time for a second-order reaction gives a curved plot. But if we change what we're plotting and we use the integrated rate equation for a second-order reaction, and we instead plot 1 over the concentration of A versus time, we get a correlation that's a straight line. Again, our y value is 1 over the concentration of A. Our x value is time. This gives a slope of k and a y-intercept of 1 over the initial concentration of A. We can now complete the rest of our table. What type of plot will give us a straight line for a second-order reaction? We've just seen that a plot of 1 over the concentration of A versus time should give us a straight line. The slope of that line was equal to k. The units on k in this case, to figure that out, we're going to go back to our rate equation. Rate is equal to k times the concentration of A squared. If we solve this for k, we get k is equal to the rate over the concentration of A squared. Putting in the units, rate has units of concentration per unit time. But the concentration of A squared has to go in as well. into the denominator. Canceling one of the concentrations gives the units of K of inverse time, inverse concentration. It's important to keep in mind the differences between rate laws and integrated rate laws. The rate law shows the dependence of the rate on concentration. Integrated rate laws show the dependence of concentration on time. In part 2 of this video, we will show how we can use integrated rate laws to experimentally determine the rate law for a reaction.